So it's a pleasure to be here. I'm going to talk about self-driving cars. I've been working on this topic for some years now. And in fact, the key issue here is how to build trustworthy autonomous systems. So autonomous systems, of course, you understand what they are. These are essential for reaching the IoT vision, where it is anticipated that we will have services and systems that could work without any human intervention. And these systems, this kind of system, are intended to replace human operators in complex organizations, and they are very different from game playing robots, any other kind of intelligent systems that are not reactive and critical, because they should exhibit broad intelligence, and they should interact with complex, unpredictable cyber-physical environments. They should harmoniously collaborate with human agents and manage dynamically many different kinds of goals. And this, in fact, reflects the transition from weak AI to general AI. So autonomous vehicles are particularly challenging technically, but this is a very interesting case because it's easy to understand. Also, I would like to say that if we are successful in building autonomous transport systems, that we will make a big step toward closing the gap between the machine and the human intelligence. Now, autonomous vehicles have been around for years, since the beginning of the 90s, as far as I remember, but over the last 10 years, this has become a very hot topic, and the big tech companies have invested heavily on that, and car industry. And at the beginning, we've been very optimistic, I would say over optimistic about the advent of this technology. And we thought that it's just around the corner, but these predictions came out not true. Today, autonomous vehicle manufacturers are revising their ambitions. Of course, this over-optimism also that still persists, and this is something I'm going to discuss. So today, there are two different technical avenues for building autonomous systems. One is to take the traditional, we know how the autopilots, for instance, for aircraft systems and things like that, but the techniques cannot provide strong transport guarantees. So both fail, both avenues fail today. And what I'm going to explain is that a lot needs to be done. And so I was saying that this is the architecture of an autonomous agent. And these autonomous agents are very different from autonomous agents you find in the literature. Beginning of this century, you remember we had this concept of autonomic computing launched by IBM. The agents were mainly software agents. Here we have reactive agents that interact with environments. So for self-driving cars, you will have an internal environment, which is the car itself, and external environments with all the obstacles for the car. So the agent receives sensory information and sends back commands to actuators that will modify its kinematic state. So this agent combines, in fact, three modules: situation awareness, so understanding what happens in my environment, decision making, so handling goals and things like that, and then knowledge management. I'm going to explain how these three modules collaborate. First, you receive sensory information. You need some perception function that will analyze, say, frames and see what are the obstacles around me. And this information will be sent to another function that will perform the situation analysis. So this function is very important because it should build a semantic model of the environment. And this semantic model is used for decision-making. And decision-making uses two functions. One is goal management. So I have to deal with long-term goals, mission management, for instance, but also short-term goals, safety and trajectory tracking. And then for each goal, you generate plans that are sequences of commands. So you have this loop, red loop here that is closed, and knowledge management is important. I think in the future should be much more important. For the moment, it is minimal because we don't know how to connect symbolic information with symbolic knowledge with digital knowledge that is generated by sensory information. So here, knowledge management will assist perception to make the right decisions, and also perhaps will provide some decision support by estimating some parameters of the goal management, and also perhaps identifying new goals, I mean, in very intelligent systems. In this slide, I explain the autonomy hierarchy proposed by the Society of Automotive Engineers. You've probably seen that. You have 6 levels from 0 level, no automation, to full autonomy. Here, what is important to note is this line of separation between level 2 and 3. From level 0 to 2, you have automation. So responsible for driving the car is the driver person, operator. And from level 3 to 5, the responsibility is on the system, on the autopilot. And I think there is a big gap between levels 2 and 3 that it will be harder to close. For the moment, we know how to build autopilots up to level 2. So I hope also this hierarchy allows you understanding what the difference between autonomy and automation. Automation means that you have automated systems that act under the responsibility of coordination of humans, while from left and up, the responsibility comes to the system. Now, let me finish by explaining why it's hard to build autonomous systems. From my definition of what is an autonomous agent, you understand you can have problems with complexity of perception. This is related to the difficulty to interpret stimuli, for instance, and to timely generate corresponding inputs. The uncertainty due to the environment, because the environment is very unpredictable, much more unpredictable than the environment aircraft, and the complexity of decision also that is reflected by the complexity of the agent's decision process, and also the complexity for generation of plans. I'm not going to give details. I think these are things easy to understand. And now let me say that once you have a very smart autopilot, you have solved only half of the problem, because you have to integrate this autopilot in a car, and this car will be integrated in a larger system that will be the autonomous transport system. So you have systems engineering issues that have nothing to do with autonomy, but these are becoming very important, and these issues are often neglected by some industrial players, most industrial players. So let me explain this. There is a concept introduced by Harel and others many years ago of reactive complexity of components of agents. And this characterizes the intricacy of the interaction of the component with its environment, nothing to do with the space or time complexity, the number of lines of code for the component. So here I'm proposing a classification of for this complexity. So you can have agents that perform a simple transformation of input data into output data, or you can have streamers that transform streams of data of input data to streams of output data, or you can have embedded agents. So this is a concept we are very much familiar now. Embedded systems interact continuously with some environment like a flight controller, but for autonomous systems, we need cyber-physical components, cyber-physical agents. What is cyber physical agent. It's an agent composed of components that contain already an embedded system. And the reason we need this for self-driving cars is because we are seeking a tight integration between the computer and its environment. So for autonomous systems, we need cyber physical systems technology, and this is something that is, okay, I mean, you have some technical problems when you deal with that. And then once you have agents and components, you have to coordinate their action. And here, an important concept is the concept of architecture, because each agent has its own goals, but of course the architecture will coordinate the action of agents so that some global goals are achieved. Typically, for instance, for autonomous transport systems, you have goals of safety, of fluidity of traffic, etc. So just a classification of architecture to see what type of architectures you need for autonomous systems. So, static architecture, given number of agents, and the interconnect is fixed, parametric. So you have a parameterized solution, and then you have a dynamic architecture. If you understand this, components or agents can come and go, and their connections can change dynamically with time. And then you have mobile architectures where you have, in addition to time dynamism, you have space dynamism. And finally, what you need for self-driving cars is what I call self-driving architecture, where you have time dynamism, space dynamism, and organization dynamism. You would like that a car, depending on its position in some organization, plays a certain role. And this is the hardest type of architecture I can figure out. So this summarizes what I said. So systems engineering complexity. You can see that for autonomous systems, you need cyber physical components, self-organizing architecture. So the hardest systems to build from a systems engineering point of view, and this has nothing to do with intrinsically with autonomy. So I think I have discussed the first item of my talk, and now let's present some ideas about trustworthiness. So why you want systems to be trustworthy? Because systems may be critical at various degrees. So system criticality characterizes the severity of the impact of a system hazard. And we know, for instance, engineering that you have different degrees of criticality. We have, for instance, safety critical systems, mission critical systems, other types of criticality. And for each level of criticality, we need a corresponding trustworthiness level. So here, just to simplify the problem, I have normalized in the interval 0-1, the levels of criticality and the degree of trustworthiness. Note that trustworthiness means, and does not mean functional correctness, means that the system would behave as expected despite any type of problem that can appear. Okay, so you can understand. So I have this correspondence between one by one trustworthiness with criticality. So for a level of criticality, I require the same quantity of trustworthiness, just to simplify. So this bisector here that some people call automation frontier divides the plan in two parts. So the green part is the part where we trust the system. So because the trustworthiness, the degree of trustworthiness is higher than the level of criticality, and here I'm explaining what happens with automated systems, and this is something you understand. So there are tasks that are not performed by systems just because we cannot achieve the desired level of trustworthiness. Now, what will happen with autonomous systems. I think that the transition from automation to autonomy will not be, will not reach suddenly full autonomy, and there will be a period, a long period, where humans will have to collaborate with autonomous systems, and here I'm giving some examples. So the key issue here is what we call symbiotic autonomy, and this poses a series of interesting problems. How human operators will collaborate with autonomous systems. There are two scenarios. One is that the human agent may override the machine decision, and the other is that the machine may proactively solicit the human agent's intervention. In both cases, there should be a carefully designed protocol because, for instance, if the machine asks you to proactively intervene, then you should have a very clear understanding of what's the situation of the system, and of course, you should be ready to do that. And this is a source of a lot of problems. This interaction between system and human is not a problem of human-machine interaction. It's a much deeper problem. It's a problem of designing the right protocol. And here, so I show this, again, idea of the division of work between a human and machine for the 5 key functions of autonomy. And of course, when this polygon will become deep blue, then we will reach full autonomy, which I doubt will be done someday. But anyway, so let me now talk about more technical issues. One is autopilot design, and the other is safety evaluation. So I said that we have, there exist techniques, critical systems engineering techniques, and we know how to build very trustworthy autopilots, for instance, for avionics. And for these systems engineers, they follow very well-defined frameworks that are specified by standards. And so they follow some methodology, they analyze requirements. I'm not going to give details. You've probably seen this V model, the so-called V model. What is important to understand is by applying these methodologies, you are using successively models, you refine the requirements, and then you have the technical means to evaluate the trustworthiness of the system. So if you apply these methodologies that are model-based, we call model-based because exactly we're using models, then you can evaluate, for instance, the safety of a civilian aircraft and say, oh, it will be at least, it will be at least 10 to -9 failures per hour of flight. So 1/1 billion, something like that. And of course, if you achieve this, then the certification authorities say, this is great, let's let the aircraft fly. Now, I said that this model-based paradigm has problems and we cannot apply it. And it's easy to understand why. Already the requirements, it's very hard to analyze the requirements for self-driving cars. It's explosive. I have tried to do that, and it's really very hard because you have to analyze even traffic regulations and things like that, and to formalize them to some extent. So the other way that is being taken by some industry is this end-to-end machine learning enabled techniques. So today the situation regarding autopilot design is that we know how to apply model-based approach to components of systems, and you have this other approach that is fully machine learning enabled. So here the idea is that you have a huge neural network that is trained. So here you receive, say, sensor information, typically frames, and what you produce is acceleration, deceleration, and steering angle information. And there are commercially available solutions. So you can buy such a system today, but I think nobody would use such a system as such in real, I mean, in commercially available cars. People will not accept this solution because of safety issues. So what I advocate personally is this idea of a hybrid design. So to combine data-based and model-based components and take advantage of the strong points of each approach. So typically, for instance, I believe that for a self-driving car, the perception function should be machine learning enabled, but for the decision, all the decision functions, I think can be. I think it makes sense to try to make them model-based, and so to have some guarantees on this side. So what I'm trying to do personally is to work in that direction. So to design an autopilot that is where all the decision-making process is model-based. And I would like to say that the hard problem here is how to build a model, a semantic model of the external environment of the car. So here you need some hierarchy of models. In fact, you start with a model that is a roadmap model, like say Google Maps. And then in this model, you can define your mission from some initial point to some destination. But then you need some more detailed maps. So that should be in some repository. And these are detailed maps of the roads and junctions you will meet in your itinerary. And this will allow you to do something that is very important, I call path planning. And then you will have synthesized local maps that will be all the static information about the external environment plus dynamic information about the obstacles. And this is information that comes from the sensors, and it should be a refinement of the lane map information. So at the lowest level, you will have trajectory planning. And there is an intermediate level I am considering very important, that this is maneuver planning, and this is what I'm going to explain in this architecture. So this is an architecture of my autopilot. I have 4 different levels. So this system generates acceleration and steering angle information for level 0. So this is, I mean, you can find this is drive-by-wire infrastructure. This is commercially available. And then you have, as I said, a repository with maps. And level 4, so you decide about mission planning, where you want to go. And this information also with the corresponding path planning is sent to level 3. So I keep the perception function outside of my architecture for the moment. So you receive information about possible obstacles and also the position of the car and its speed. So from this, you can generate what they call a safety envelope and the path planning. So the path planning is on the lane map, from which now you will provide information. The envelope is very, very important, and the information about the path. And this is sent to level 1. So level 1 is about collision avoidance and trajectory planning. So this is quite, I mean, this is the easy part. And then the hard part of this system is to design protocols, maneuver protocols. And here we have distinguished something like 10 to 15 different maneuvers. So a maneuver protocol says how you behave in order to overtake, for instance, how you navigate in a roundabout or in a parking. So the key idea here is that the driving skills can be obtained as the combination of these protocols. And of course, this is something that should be proved. Okay, so let me move on and talk about validation. So probably you've seen in the media declaration like this one that my Autopilot has been tested for so many billions of autonomous miles and it's good enough. So an important question is how we validate autopilots today. And let me say that this type of arguments is substantiated by, okay, they try to substantiate it by using some statistics, in fact, and some reasoning, some statistical reasoning. So for each country, you have statistics about the rate of accidents of a certain type per driven mile. So here in this table, so you can evaluate by a simple statistical reasoning how many miles you can drive, you should drive without fatality, for instance, in order to have a 95% of confidence level that this will happen. And of course, you can have make similar reasoning for other types of accidents. So, I mean, this is nobody doubts about. I mean, this is just mathematics, that's reasoning, but still there is an open issue whether this miles argument is technically tenable. And let me give you my opinion. Of course, global system validation will be achieved only through simulation and testing. There is no doubt about that. I'm saying this because there are papers where, I mean, people try to verify or say that simulation is not good enough. Unfortunately, simulation is the only way we can validate such complex systems. The important question here is how a simulated mile is related to a real mile. And these people who advertise these achievements of billions of miles do not explain how a simulated mile is related to a real mile. And this is a problem, because any reasoning of this type, any argument of this type, any connection should be model-based. So you should have a model to explain how many different situations you have encountered in your simulation, because you can imagine, of course, that you can simulate cars in highway conditions, ideal conditions, and of course you can drive for centuries and nothing bad will happen. So we need a validation theory based on some model, and the model should allow to define some concept of coverage. For instance, if you want to verify, say, some piece of software, to test, sorry, a piece of software, you will have a coverage criterion and say so many instructions of my code have been executed, or so many branches have been executed. So you have some arguments about that. And something else that is very important is the use of scenario for this type of testing. Why? Because scenarios are used to bring your system to particular situations. And the scenario try to control the system. You have some parameters to control the system, and you try to bring it to high-risk situations. And of course, something else that we are missing today is verdicts and diagnostics. You see, in all of these simulators, they say they give figures about potential casualties, potential accidents, but they don't explain why. For instance, it would be interesting to know how many violations of traffic regulation we have, but formalizing traffic regulations and understanding what is a traffic regulation in a simulator is a real problem. So, just to summarize, I will say that whatever design approach you take, simulation is very, very important. And so the simulation should be realistic. Realistic meaning that you you are faithful to what is the real environment, because you can have some very simplistic simulators, but also it should be real. Real means that the execution mechanism respects the laws of physics and geometry. And it happens that some industrial simulators are realistic because they are using game platforms. So very realistic, but they are not real. And I have examples of this. For simulation, we need realism, or we also need some domain-specific language for modeling. This is very, very important because these systems are very hard to model using general-purpose programming languages. You need some specific notation. I mean, it helps a lot. And then you should have what I call semantic awareness. The user of the simulator should understand the system semantics as the behavior of a machine that has well-defined state. Why this is important? Because you want to replace some sequences. So you want to set your system to a particular state. And also you should have concepts of what is controllable, what is uncontrollable. And also, I think that you should be able to execute at different scales, time scales and space scales. So this is a big challenge, simulation. And of course, performance of the simulator is an issue if you want to do some detailed analysis. And this is something I'm not going to discuss because I have no time. Now, it's time to conclude. And to conclude, I have 2 slides. One, to say that we should understand that, at least as far as situational awareness is concerned, humans can do much better than neural nets. So we should never replace a human by a neural net, I think, for the moment. And let me explain why. Because our mind is equipped with a semantic model of the world, and this model is enriched since our birth, and we have a huge network of knowledge, and we cannot be fooled as, for instance, some autopilots can be fooled, and there are many papers about that, how you can fool neural nets. And the reason is that human understanding combines bottom-up reasoning from sensor level to some semantic model, the semantic model of our mind, and top-down reasoning from the semantic model to perception. So if I see this stop sign here with some snow, so I receive this sensory information, and with now at semantic model level, I know that the stop is an hexagon and it is red, and it's okay. I know the characteristics, so I conclude that it's really a stop sign. Or if I see this aircraft here hitting the ground, no need of theory or special training to understand that this is an accident. Or if I see this guy here with a child, and they tell me this is a father with a baby, no need to tell me who is the father, who is the baby. So I think that humans are very strong at that, and we should not, I mean, we should not underestimate this, and we should not neglect this. The second type of conclusions I would like to draw is that trustworthy autonomous systems, and in particular self-driving cars, are not only about intelligent agents. All these systems engineering issues are becoming very, very important. And also that the monolithic solutions preclude safety guarantees and will not be accepted, in my opinion, although there are commercially available such solutions. So I believe that hybrid design is the right approach to find compromises between performance and trustworthiness. And then about system validation, I would like to say that we need, simulation is a big challenge, And of course, any safety evaluation should be model-based. We should have a model to justify that the test that we are doing is the test we are doing cover the most relevant situations, and the system is good enough. So just to summarize, I will say that there is a big gap between automated and autonomous systems that we have underestimated initially. And I would like also to say that this autonomous hierarchy I have presented is a bit misleading, because you have these 6 levels and you have the impression that the difficulty in climbing up this hierarchy is evenly distributed over the 6 levels. There is a huge gap at level 3, and also level 3 where the autopilot is supervised by a human. This is, I think it's a very hazardous idea because of the problem of interaction between the human and machine. So there are a lot of problems to be solved before we meet the challenge. And for this, we should develop a new scientific and engineering foundation. This will take some time. So thank you for your attention.
Thank you very much, Joseph, for sharing your insights with us and for sharing your thoughts. So a reminder to everyone, since we have so many participants, so either you can post the questions in the chat or in the link that I shared with you several times already. And we have several questions that have come in, and I would start with a question that is the most rated, and I think was the first that came in. The question was, do you see LiDAR solving level 3 or level 4 autonomy in unfenced regions within the next 5 to 10 years?
I think that we are closer to level 4 than level 3. This is a very good question. Why? Because all the problem with the self-driving cars comes from the non-predictability of the environment. We know that there are very interesting experiments, in particular in Europe, where we will have platoons of cars in highways that are adequately instrumented. So, I mean, this is very close. It depends. I think that the problem of self-driving cars would become much simpler if we have the adequate instrumentation. You can understand this. The problem comes from perception. Now that I think that most industrial players push in the direction of AI just because they want to sell the results and get some advantage, competitive advantage. But for sure, level 4 is for tomorrow. And perhaps level 3 is too dangerous if we cannot solve, you see, the problem of interaction between machine and computers and autopilots and human operators is already understood very serious problem in aircraft. You have, this is a source of accidents already in aircraft. Why? Because there are, for instance, situations where suddenly the pilot disconnects the autopilot because he thinks he's doing the wrong thing, or I mean, it's a source of problem. So another solution would be that we go directly to level 5. It would be much simpler. Okay.
It actually
level 3 is very dangerous anyway.
But some developer or some developers are trying to do that, so trying to jump directly to level 5, or at least that's what they're claiming to do.
Yes, I think this is more reasonable, but in this case, this means that, yes, skipping level 3 makes sense, and go to level 5 if you can enforce some rules about the environment. For instance, if tomorrow we decide that everywhere we have fully autonomous cars, level 5 would be much simpler. You see what I mean?
Yes. So thank you for the answer. We have a very popular question, and So Pierluigi is asking, it seems to me that you're saying that machine learning has no real future in self-driving cars. Is this correct, or I misunderstood?
No. What I'm saying is that machine learning is, I mean, you cannot live without machine learning for perception, this for sure. Then also machine learning can be very useful for adaptive decision making, because we can, by using machine learning, better understand the characteristics of the environment. So machine learning has a future. But what is a problem is these monolithic solutions where we don't understand what machine learning, end-to-end machine, I think has no future. We have the proof today. We have commercially available products that are end-to-end machine learning. I think nobody would accept using these products. The future is hybrid. And the problem is how to make collaborate model-based, because we have very good algorithms for trajectory tracking, collision avoidance. So we have some solutions for the problems, I mean, for the basic problems. And then, of course, we should put all these solutions together with some perception and the knowledge management module and integrate all this.
I think there's another question that suits to it actually quite well.
Sorry, and the problem is not to build a single autopilot. The problem is how to make sure that this autopilot will collaborate with other autopilots and things like that.
Yes, because this becomes system of systems, actually. Yes. So we have another question that suits quite well to it, because you were advocating actually to use model-based for system validation. But what if we don't have a model, and how can we make actually a safety case then? And because this is what we then need to do to obtain homologation for the systems. So it's clear if we have models, but what if we don't?
But in any case, I mean, any reasoning, any type of reasoning is model-based. I mean, by construction. You see, in the human mind combines two types of reasoning. Okay, one is procedural reasoning, it's model-based, and the other is unconscious. Okay, so if you reason, you are model-based. You explain. And in order to explain, you meet, of course, the model can be explicit or not, okay? But there is a model that should be, or you make a case analysis. But, and of course, the problem for AI today is how to make it understandable, how to make it explicable, okay? And for this, there are papers, there are people working in that direction, how to make AI explainable. But what it means that you extract a model of the neural net and you can reason about that. In all cases, you need a model. Even if you take a design approach that is end-to-end machine learning enabled, when you want to provide some argument and say, now I have tested my system, a certification authority will ask, how you have tested your system? Show me that you have covered all the difficult situations. And we should provide an argument based on a model. What are the possible situations you can encounter? So you will say, in a roundabout, it will behave like that. And so you have to, I mean, any argument is model-based.
Yeah, there is also a question that suits to it quite well. So how does or should the model incorporate human behavior in different external environments, particularly human behavior cultures, pedestrian drivers, etc.?
Sorry, I'm not sure I got the question. So
how should the model incorporate human behavior in different external environments, but also integrating that?
Yes. How the model should incorporate human behavior?
Yes.
Well, I think you can have
because you're advocating the simulators and
yes,
but then,
of course,
but
yes.
then you
So
also
at some
need
point,
to model.
yes. So at some point, you will show some pedestrians and things like that. Now, human behavior can be very, very complex, very, very complicated. So at least you should try some, I don't know. I mean, this is a hard question. Once you deal with human behavior, you encounter problems. Like, for instance, in security. Security is a problem we will never be able to solve. Like safety, at least when we know the environment, the physical environment, because security, you have, I mean, a human human inventivity, humans can be unpredictable. I mean, they have imagination, but you can figure out what can be a normal pedestrian behavior. Okay, but this is simple to model.
There has been a question that has been the most popular. So the question is particularly on on how realistic machine learning actually is. So the question is: generative models can produce original realistic images from text.
Yes.
It has been shown recently. Isn't this evidence that deep neural networks can capture semantics?
No. I mean, because semantics means that you have a model. Semantics does not mean that you synthesize a picture or something like that. Semantics means that you have a model.
Yeah, but it seems to learn implicitly the model.
One thing is to learn the model. The question, yes, okay, so it learns a model, yes, but what's the proof that it learns a model? Yes, okay, so it learns a model, but it always learns a model. I mean, even all the data sets are models. I mean, that they are simple models. Okay. The problem with machine learning is how you understand the behavior. Okay. And so the problem in general is, I mean, if I can try to explain this in more abstract terms, the problem is how to connect digital information, digital knowledge, or sensory information with symbolic information. So you need a symbolic information about the behavior because you want to learn about that, okay? And for this, we don't, of course, there are some papers about that, but it's because, okay, so the problem is I have a neural net. What I can do in theory is to try to extract a model that is a kind, because a neural net has an I/O behavior. Okay, so an I/O behavior, you can try to build a function that characterizes the I/O behavior. I know this is a hard problem. In some cases, this is tractable for some types of networks. But even if you characterize the I/O behavior by a model, then you should, so by a mathematical function, this is not always possible, because if my neural net distinguishes between cats and dogs, what's the mathematical model of a cat or a dog? So it's, of course, if my neural net deals with numerical data and things like that, then perhaps there is a solution to the problem. But you see, the interest also of neural nets is that they can deal with concepts that are not easy to formalize, like cats and dogs, or pedestrians.
But does everything need to be formalized in order to?
No, I said no. Not everything needs to be formalized, and this I explained. But when you simulate, you should have a model that is an abstraction of the world and say, well, my car has encountered, so this model will say what are the hard configurations, the hard traffic configurations. So you should have some arguments. You are not obliged to model perfectly the behavior of a pedestrian, but you are obliged to explain what are the hard situations and how you deal with different hard situations. And of course, the situations should be based on some realistic model and things like that. But you need this, you need some argument.
Thank you for answering to these questions. The next question is, how can we prove that machine learning decisions are safe?
Machine learning decisions are safe. So in absence of models, we cannot. In absence of models, we cannot. But what we can do, okay, let me try to be a bit more positive. So there are some solutions now where you say, oh, machine learning is quite good. I cannot guarantee safety. But let me have a solution where I have, say, a controller which is machine learning based that works in parallel with another controller that is less sophisticated but can guarantee safety. So I have a switch, I let the two systems work in parallel, and this is a realistic approach, okay? I've seen implementation of this for cars. So you will run the two systems in parallel with a switch, a reliable switch, and in critical situations, you disconnect the neural net and you take over. I mean, not as simple as that, but you the safe controller will take over. Of course, I mean, it's not as simple as that, but I think that this is an interesting principle. And this also, so in that case, you don't need any argument about the safety of your neural net, of your AI-enabled system. You just use it, and then you have a less sophisticated system that is safe, that can take over. Of course, the problem is, okay, the collaboration between the two systems, as I explained.
There's the next question that is, can you put the challenge of designing safe autonomous vehicles in the context of the challenging proofs, for example, the Fermat's last theorem?
Oh, why the Fermat's last theorem has to do with designing autonomous systems?
This is in the context of challenging proofs, but maybe the person
yes,
who
asked
it.
These are different worlds, because one thing is the world of mathematics. So in the world of mathematics, I mean, once you have proven that Fermat's last theorem is true, of course, somebody should carefully read your proof, and it took some time to people to read the proof to make sure that this is a really valid proof. But and this will remain or stay there forever. This is mathematical truth. And now we are talking about, you see, there is a big difference between mathematical truth. This is eternal, and then the other is what is technically right. What is technically right is different. It's, of course, you rely on mathematics, you have some arguments, but also you rely on the physical world and on the properties of the physical world. It's a different kind of problem. And of course, I think it's very challenging because, as I said, if we are successful in having very good autopilots, this means that machine intelligence will get very, very close to human intelligence, because human intelligence is about that, about how you combine different skills all together. This is, yes, but this is a very different kind of problem.
I think we have just 1 minute left. I don't know if you have, we have still open questions. Do you have some additional?
As far as I am concerned, I have time, but it's up to you. Yes, I can take questions. Yes.
Okay, so if anyone has to leave, just feel free to go ahead and leave, and we will use the opportunity that you're agreeing to answer to additional questions. And one of the questions that we have is, will a design to minimize human-machine interactions be easier to trust, such as self-driving subway train? Do you think about future transportation? What do you think about future transportation?
Oh, okay, no, these are too many questions for me.
So
I'm
sorry,
not sure
I will.
understand. Yes. Yes,
Sorry,
okay.
I will start with the
Because
first.
I mean, you talked about trains. I mean, trains are automated systems. That the way we use trains these are automated systems. We know how to build very reliable automated trains. I mean, of course, you can say this is autonomous, but you see the difference between autonomous and automation is autonomy and automation is that for autonomy, you combine very different function. Control is not statically computable, you see. While for trains, the control is statically computable and you have very well-defined goals. And of course, if the environment is predictable, as it is often the case, then it's a simple problem, trains.
So, but I guess how I understand the question, so actually trains are designed to have, well, rather limited human-machine interactions, and it has been decreasing over time as well. So do you believe that they are then easier to trust? So if Elvis asked the question, if you would like to clarify that, please type addition into the chat.
So trains, I think that we can know how to build very trustworthy automated trains. I don't see what is the issue here.
But even but even railway industry has been pushing towards autonomous trains, and yes, so they're already quite automated.
Yes, but autonomous trains you have yes, but this is. I think there are already autonomous trains, or to some
yes,
extent.
but particularly for
at
subways,
least you have
yes.
autonomous subway.
Yes.
For subways, yes. I don't think that. Of course, it's always good to have some human that supervises, so you can automate plenty of functions. And but you see, the problem for trains is much simpler, and it is simpler just because, of course, the environment is much more predictable, as the environment for aircraft also is more predictable.
Yes, so thank you for this answer. Where would you sort in SAE FSD beta from Tesla's latest update?
So SAE
level?
What's the question? Sorry.
Where would you sort
yes.
in the FSD beta from Tesla's last update in terms of the autonomy levels?
Oh, Tesla's last update. So you see, this is a delicate. I mean, okay. I fear I cannot answer this question because it's about what Tesla is doing, and there are many. Yes. Okay. I mean, there is no agreement about the evaluation of what Tesla can do. So there are some. So in the media, you can read some articles where they say that they are over-exaggerating the performance of their cars or their reliability. I don't want to say anything about that. And they don't clearly say this is, of course, they say our car has autonomy features, or okay, I mean, there are some ads about that, but they don't say this is level 5 clearly. But also there is another problem here, because there are no standards for cars. There are no for autonomous cars, I mean. And you know that in the United States, they accept what they call self-certification. Self-certification means that the industrialist, I mean the manufacturer, the car manufacturer says, oh, my car is good enough. And this is the case for Tesla, which is a strange practice. And to the best of my knowledge, this is not accepted in Europe, self-certification. So it's very hard to know. I mean, in absence of standards, it's very hard to know whether Tesla's cars are compliant to any rules or whatever, or what they are doing.
Thank you for that comment. There are two questions on hybrid approaches, and one is, can you give some reference to the hybrid approaches? And the other
this
is
actually my terminology. This is my terminology. I cannot.
But the other question is also connected to it, because there are different hybrid approaches that combine machine learning and physical models. Do you see any of them that is the most promising, or which is, from your perspective, the most promising?
Well, what I call a hybrid approach is that I combine model-based and data-based. That's what I call hybrid approach. Because the term hybrid also is used in other contexts. Probably there is a misunderstanding. So what I call hybrid approach is the combination of, say, neural nets and model-based decision-making systems, something like that. Okay.
Okay, and there is one last question, at least up to now. Is language easier or more difficult to solve with AI than self-driving cars?
Is language
easier or more difficult to solve with AI than self-driving cars? So do you consider solving the understanding language, is it easier than self-driving car than?
These are two different problems, perhaps equally hard. I mean, if we can understand, you see, if we can understand language, I think we would be able to, because really understanding language, natural language, means that you know how to build this semantic model we have in our mind. So we have a semantic model of the world, and when we speak, we exchange messages, we know how to interpret on this semantic model. And yes, so I consider that the problems are equally hard. And if we know how to solve the problem of language, natural language understanding, then a good deal of the problem of autonomous cars will be solved. Of course, you have all the engineering issues also to address. Yes, good question. Thank you. Thank you.
Thank you very much. I think we did not have many more questions. I would like to thank you for the time that you took, for the honor that you accepted the invitation and started the first series, or the series of the webinar. So thank you very much once again, and have a good evening.
Yes, good luck to everybody. Thank you. Bye.